In the same way we use linear models to describe the relationship between one response and one explanatory variable, we can expand the same concept for multiple explanatory variables. In the example of the phone bill cost, we have one response, the cost, and only one explanatory variable, the time used. Now let's compare it to a slightly modified situation, the electricity bill cost. In this case, the monthly cost is 15 cents per kilowatt hour use between 7 p.m. and 7 a.m., plus 30 cents per kilowatt hour used between 7 a.m. and 7 p.m. The cost depends not only on the amount used, but also when it was used. In this example, we have one response variable, the cost, as a function of two explanatory variables. The multiple linear regression models follow the general form, the response variable y, as a function of the independent coefficient and k explanatory variables. For example, a linear model for two regression variables has the form y equal to beta 0 plus beta 1 x1 plus beta 2 x2. However, not every system has a linear behavior, even though we still can use linear models to describe them. For instance, a model with two regression variables that interact with each other has a nonlinear term, x1, x2. However, we can linearize it by using an auxiliary variable x3 equal to x1 times x2. This way, the nonlinear model with two variables and interaction becomes a linear model with three regression variables. The same idea can be applied for quadratic models. Here we have the general equation of a quadratic model for two variables with interaction. The response y is represented by the independent coefficient plus the linear terms plus the quadratic terms plus the interaction. In the quadratic terms, the response varies with the square of the explanatory variables. They are used to model curvatures in the response's behavior. Similarly to the model with interaction, we can apply transformations to linearize a quadratic model. Let's make x3 equal to x1 to the square, x4 equal to x2 to the square, and x5 equal to the product between x1 and x2. As a result, we have a multiple linear regression model with 5 explanatory variables. The parameter estimation for multiple linear regression models follows the same steps of a simple linear model. Here we have a table with a general response variable y and k regression variables x1, x2, x3 until xk, and the general equation for the multiple regression model. The system can be represented by using matrix notation. The y matrix of the experimental results equal to the product between the x matrix of the regression variables and the beta matrix of the regression coefficients, plus the epsilon matrix with the errors. We calculate the beta hat matrix of the estimated coefficients as the product between the inverse of x transpose times x and x transpose times y. The analysis of variance will test the significance of the regression. The null hypothesis will be rejected if the p-value is lower than the level of significance. The rejection of the null hypothesis indicates that at least one regression coefficient beta j is different from 0, meaning that at least one of the regression variables xj contributes to explain the variability in the response. However, the ANOVA table does not say which regression variables affect the response. We can use multiple linear models to analyze any kind of dataset, design or not. In the case of design experiments, the multiple linear regression model approach has several advantages over the traditional analysis of variance. Suppose that we have a missing observation in a 2 in the power of k design. It can happen for several reasons. We cannot use the traditional analysis of variance with a missing observation, since we don't have the results for one of the treatments. However, we can still analyze the experiments by the regression approach. Regression models are also suitable for analyzing designs with inaccurate levels of the factors, as we are going to see in the next example. Also, it is possible to calculate the model's lack of fit to verify the linearity of the model. And if nonlinear, we can build second order models to fit the response with the regression variables.